Today, we're diving into one of the most fundamental rules in the entire universe. Seriously, it's the rulebook that governs everything from a star exploding to the battery in your phone. It is the first law of thermodynamics, energy's unbreakable rule. Now, you've probably heard this line before, right? It's the absolute core of it all. This one sentence is the foundation we're building on. It tells us that the total stash of energy in the universe is fixed. It's always been here. It's always going to be here. It just, changes its outfit from time to time. And that's the real puzzle, isn't it? I mean, if energy is constantly shifting around, changing from heat to motion to chemical energy, how in the world do you keep track of it all? Well, to follow the energy, you need a system for bookkeeping. And it turns out the universe has a surprisingly simple one. To make this super simple, we're going to use an analogy you already know, a bank account. The energy inside any system, whether that's a car engine or a chemical reaction, is just like a bank balance. You've got what's in the account, and then you have deposits and withdrawals. So let's meet the three key players in this transaction. First up, we have internal energy, which we call U. This is literally all the energy that's already inside a system. Think of all the kinetic energy of its molecules, all that buzzing and vibrating and bonding. In our analogy, this is your account balance. It's the total amount of cash you have in the vault. Next up, heat, or Q. Now, this is energy on the move. It's not just sitting there. It's energy crossing the boundary because of a temperature difference. So if your system gets hotter, it's absorbing heat. That's a deposit straight into your account. If it cools down, it's releasing heat, and that's a withdrawal. And our final player is work, W. This is another way for energy to cross the boundary. If the surroundings do work on the system, like imagine you're compressing a gas with a piston, you're literally forcing energy into it. That's a deposit. But if the system does work, like that gas expands and pushes the piston out, it's spending its own energy. And yep, that's a withdrawal. Okay, this part is absolutely critical, how we sign our transactions. The convention comes straight from our bank account analogy, and it's dead simple. Anything coming in is positive, anything going out is a negative. So heat absorbed by the system, that's a plus Q. Work done on the system, that's a plus W. They're both deposits, increasing the balance. On the flip side, heat released is minus Q, and work done by the system is minus W, both withdrawals. Getting this sign convention right is the key to the whole thing.
All right, so we've got our account balance, U, and we've got our transactions, Q and W. So now it's time to put all the pieces together and build the master equation for the first law.
So think about it for a sec. If you know your starting bank balance, and you know all the money that came in and all the money that went out, how would you figure out the change in your account? It's really, really simple, right? And there it is. Delta U equals Q plus W. The change in the balance is just the sum of all the transactions. That's it. This incredibly elegant, powerful little equation is the first law of thermodynamics in its mathematical form. It governs literally every single energy transaction in the cosmos. So let's just spell it out to make sure it sticks. That triangle, delta, means change in. So the change in your internal energy, delta U, is simply the heat you add to the system, Q, plus the work done on the system, W. Here's the big takeaway. Your internal energy can't just change by itself. It has to be because energy crossed the boundary, either as heat or as work. Okay, so the theory is cool, the equation is neat, but let's see this thing work in the real world. This is where the magic really happens. We're going to apply this blueprint to 4 really common scenarios you'd find in any chemistry or physics lab, and you'll see just how powerful it is. We're going to put our equation to the test under 4 different sets of rules. What if we lock the temperature so it can't change? That's an isothermal process. What if we wrap the whole thing in a perfect thermos so no heat can get in or out? That's adiabatic. Then we'll look at what happens with constant volume, called isochoric, and constant pressure, isobaric. Let's see how our master equation adapts. And check this out. This is where the sheer elegance of the law just shines. For an isothermal process, if the temperature is constant, the internal energy doesn't change. So delta U is 0. Our big equation just becomes W equals negative Q. Any work the system does has to be paid for by the heat it absorbs. Now what about adiabatic? We block all heat, so Q is 0. Poof! The law simplifies to delta U equals W. The only way to change the internal energy is by doing work. And for isochoric, constant volume means no expansion or contraction, so no work is done. W is 0, and the law becomes delta U equals Q. It's just that simple. The same rule elegantly adapts to every situation. So, at the end of the day, what's the big takeaway here? The first law of thermodynamics isn't some abstract theory. It's a practical, powerful tool for bookkeeping. It's the universe's own accounting system, making sure that every single joule of energy is accounted for, no matter where it goes or what form it takes. And that leads to one final huge thought. If the total amount of energy in the universe is a fixed number, a constant that can never, ever change, what does that actually imply for the ultimate fate of everything? The energy won't vanish, that's for sure. But how it gets distributed and how useful it is, well, that's a whole other story.